Hey, good afternoon, everybody. I'm Eric, joined by my teammate, Will. Over the next 45 minutes, we're going to talk about how Mapbox the team at Mapbox is building the most beautiful map in the world, and how we're doing it on AWS. So while this is specific in terms of mapping, what Will and I, our goal of this talk is to make sure that we abstract out some of the core concepts that work for us real well within AWS. And that's everything from storing on I see a couple familiar faces in here that are doing a lot of work on the big data side. For us, big data means stuff that's hard to work with. And right now we're managing about a petabyte of data in S3. And that's got to be redundant, and it's got to be accessible. In terms of how people access this data, we're serving out tens of billions of map tiles across hundreds of millions of users, and literally all around the world at scale. 5:30 in Vegas is 4:30 in the morning in Moscow. That gives us about 2 hours until 40 million Russians start waking up and hitting our maps. Over the next few hours, the other 40 million of VK.com users in Europe are going to start waking up. The French wanted their maps on Le Monde in French. They start hitting us. Then Financial Times and somebody wants a coffee in New York, right? Literally, our server logs look like a respiratory system for the world, and being able to scale that. And scale that totally in an automated fashion, low cost. And scale isn't just about serving out the imagery, it's also about processing the imagery. And that's why I want to spend a lot of time today talking about, specifically in context of working with imagery from NASA and other open data sets. So before I get into telling a story about how we're working with satellite imagery here and how we're using the AWS services, I just want to put this into context of why we're trying to make the most beautiful map in the world. Mapbox is a platform for developers and designers to go make whatever kind of map they want. We have over 5,000 platforms paying us right now to be core center of their geo experience. And that's everything from helping figure out where you can find pork and whiskey to figuring out where the Iranian nuke plants are on our cloudless satellite atlas. Satellite imagery is obviously key on the mapping side, right? And our team, the way we actually don't have any satellites, as much as we pretend we do sometimes. We source it. But this is our imagery, right? This is imagery that we've collected. This is aerial from USDA, for example, that we've collected, processed, color corrected, and turned into a totally interactive map. And where we don't have access to open data from different countries, we source it from our friends over at Digital Globe, the largest satellite company in the world. And so I want to spend a little time talking about what this pipeline looks like and how we work with this with AWS process. And parts of the pipeline aren't always sexy. Again, you're talking about moving around terabytes of data. This is Chris and Charlie and Bruno packaging up. I think this was 48 terabytes of imagery, and putting in a box for FedEx and shipping it SneakerNet to AWS with the API key on the side and getting it scanned and processed in there. So while this process is not necessarily pretty, what's inside is absolutely beautiful. We've got, using things like NASA's imagery from MODIS, we've got a daily snapshot of the entire world. Now the problem with that snapshot's, in this case, the clouds, right? So what we do, instead of just working with a scene, we take many days of imagery and pull it back and make a whole cube, right? And then we spin up thousands of servers and filter the cube. So now you got the clouds on the bottom here, you just throw away all the white part. You got a smaller cube, right? Then on a pixel by pixel basis with that smaller cube, we look for the most cloud-free and newest pixel, and then slam it together to make the most perfect summer day anywhere in the world with no clouds. This isn't just about making a pretty map. This is one of my favorite maps captured by Charlie. I mean, this is what cows look like from space. That's not a scene. That's an international border showing different land use patterns. Literally livestock walking up and eating differently. What you can see when you can start processing imagery like this is incredible. I mean, why is Australia so red? Processing imagery out like this is where it gets hard, right? Doing that level of atmospheric correction and declouding. One of the more interesting graphs that I saw from the team was this. Let me break this down, and this is the most important example of how we're really leveraging cloud. We've got our declouding algorithm running across a couple hundred EC2s, and it's not running as fast as it was supposed to, right? As fast as we benchmarked it. So what we're able to do, we're able to throw out those EC2s because we're buying them on the spot market. Tweak the algorithm a little to run on a different model EC2, and we start killing it. Unfortunately, the spot price increased, so our server shut off. So we stopped for a second, increased our bid point, and then went on to go kill it. And what you get from this process is just absolutely stunning. Being able to see this level of detail all around the world, and that means we're able to serve out folks on the ag side to looking at fracking happening. Our water usage patterns, especially in the West right now, are crazy. I love this. It's just like the red tone in the hills over down in Mexico. This is South Africa. In short, AWS has given us the ability to side-by-side out-process giants, right? Folks that absolutely understand cloud. And what we're able to do by having a great base map and having a better base map than anybody else is put out these building blocks to let people do totally crazy stuff. I mean, this is our satellite base map. And here, Skybox, a small satellite company, took the first HD video from space, right? That's 2 million feet up, and overlaid it on top of our imagery. You can literally see the cars moving here, right? And so we're kind of like this glue layer where people with their own private data can upload that to our platform, and we serve that out and integrate it. So that's why we're building this base map. I had the pleasure of getting to radically simplify how well this works. The reality is this is really hard, and to get into some of the specifics about how we're leveraging technical details around Amazon, I want to invite Will up.
Nice work. Oh, thanks. Thanks, Eric. Yeah, so I want to walk through two strategies we use on AWS to do data processing and data distribution. Now, the image that you saw earlier in the talk with all the clouds, that's we get one of those images every day for 2 years, and that's how much data we need to feed into our algorithm. Each one of those images is over 17 billion pixels. So if we multiply that image by 365 days and then multiply that number by 2 for 2 years, we end up with more than 12.5 trillion pixels on our hands. And we have to go pixel by pixel through each one and find the best one. Find the best pixels in this massive haystack. That's a lot of pixels. So what do we need? We need data processing, computing power that we can scale up and down. I'm sorry, we need to be able to quickly distribute massive amounts of data, process massive amounts of data, and we need to do it at a really low cost. So I want to start with processing first, then move on to distribution. So processing, we need a massive amount of storage for both our source data. This is the data coming from NASA, either via FedEx or it's coming from USGS. There are a variety of sources. We can get it from a commercial provider, but it's coming on hard drives, it's coming over FTP, but basically what we need to do is get our source data into S3. We also need a massive amount of storage, as Eric said, almost a petabyte of data storage for our processed outputs. And I'll talk about that a little bit more. We also need a massive amount of computing that we can turn on and off multiple times a day, completely flexible, and it needs to be very quick to come online, and then we want to shut it off very quick so that we can stop paying for it, because it's expensive. And then finally, everything needs to be fully automated. I don't want to come in every morning and push a button. I don't want to be babysitting a stack. We need to run this stack all the time, and it needs to be humming along, and it can let us know if something goes wrong, but most of the time it needs to be just doing its own thing, keeping up with the data. So going back to one of the earlier slides in the talk, there are really 4 services we use to accomplish this. The first one is obviously S3, then EC2. The new ones are auto-scaling, which is allowing us to dynamically control the number of EC2s we're running based on any number of metrics. And I'll get into the details there. And then SQS, which allows us to queue up a set of jobs and then work on those jobs either one at a time or in parallel. And as we spin up more computing, we can process more of them faster. So here's what we built. We're starting with the NASA server, but again, this can be anything. This can be a FedEx truck. It can be another public data source. It can be a commercial data source. But for the purposes of this, we're just going to stick with the NASA server. So imagine this is an FTP server. And we have this watcher instance. And this is the first step in the flow. So what does the watcher instance do? Its job is to copy data, scan NASA servers for new objects, new files on NASA servers, and essentially cache them to S3. It also does a little bit of inspection in the file and logically splits those files up into smaller parts so that we can parallelize and process those parts in parallel. Why would we want to stash a file on S3? There are really 3 reasons for this. One, we want to take advantage of the incredibly low latency between S3 and EC2 in the same region. So if you're in US standard S3 region and you're in US East 1 AWS EC2 region, your latency, your bandwidth between S3 and EC2 is extremely high. You're going to be able to transfer files, get them on the box fast, which is really important when you're scaling up to hundreds of instances and you need to get your source data on there quickly. And these source data files are massive. We also don't want to hammer NASA servers, they're FTP servers. If we kept from every single worker, again, we have hundreds of them, we don't want to make an FTP request to NASA servers and effectively DOS their service. We like them, they're providing us awesome data, flying satellites in space and stuff. Also, it's pretty straightforward. We want to be able to reprocess the data in the future if we ever need to. So having it in our S3 bucket, we know where it is, we can catalog it, we can store metadata about it, and we can easily just pump it back into a new algorithm if we improve something. So we just like to keep it on S3. And now going back to that watcher instance, another one of its jobs is to split up one massive file into messages. These messages go into the SQS queue, and SQS is the simple queue service. And again, it just manages how much work you have. It keeps track of how much work you have to do, and is responsible for dishing out that work one at a time or 2 at a time, depending on how many workers you have, how many EC2s you have working on your workload. So one of the things that we learned very quickly about structuring SQS messages is shorter is better. It's always better to have a 5-minute message, a 5-minute task, than have a 45-minute task, because if your task fails in minute 44, you have 44 minutes when you go to retry that. You have to play a lot of catch up. So shorter is better. We found that around 5 minutes or less even is pretty good for this kind of work. Also, your messages need to be repeatable. And that's helpful if if you have a lot of failure, latency goes up, error rates go up. It just happens. When you're doing data processing at this scale, you have 3 nines of availability, but when you're processing trillions of objects, that margin is actually comes back to bite you. So you have to be prepared for failure and architect for failure. And one way we do that is make it so that messages are always repeatable. We don't want to be corrupting our data set by processing half of a message and then reprocessing it and having a mess on our hands. And just to illustrate what we do with the raw data, we actually have one file and we just logically split it up into separate messages. We don't split the file up itself. We just basically generate 100 or 200 or 300 messages, each with a different index. Here's what they look like. I've just called this property, this looks like JSON. I've just called this property scene. And it's basically just, think of it as like an index or a position in the file where when a worker gets this message, that worker knows that it's going to work on part 730. And the next worker gets 731. And then it's going to return the message to the queue. This is a technique we use to get to that 5-minute task duration. So going back to our flow diagram, that's the watcher EC2. Let's talk about, the watcher EC2 goes into S3 and SQS Cube. The next step are these worker EC2s. So you can see in the diagram it's represented as 3 of them, so we're running multiple of these workers at any time. One of these workers has sort of a workflow that happens on the box. The first thing it does is grab a message from the queue, and we just saw what those messages look like. The message contains a path on S3 of the raw data, and then it has a path where the outputted data should go when processing is complete. So we grab that message, we grab the raw data, we run our algorithm, and I could do a whole other, or not me, but Mapbox team could do a whole nother talk on the details of the types of image correction algorithm, atmosphere removal algorithms that we're running on the EC2s, but I just wanted to stay high level for this talk and talk about the mechanics and how we're touching AWS tools, essentially. But we're running Python scripts, Node.js, and C++ for the most part, and we're using a lot of open source tools to actually do our image processing. When the image is processed, we just put the files back on S3 at our output destination, as described in the message. And then we just delete now that we know that the entire job is finished, we can delete that message from the queue, and that message will never appear for any other worker. So this is one worker EC2 instance, but there are 3 worker EC2s. These workers are actually part of an auto-scaling group, which is pretty key to how the entire workflow works. Auto-scaling allows us to control the capacity or the size of our cluster based on the number of messages in the SQS Cube. And this is really important because it sort of goes back to the automation that I was talking about before. We don't really want to have to think about how many EC2s we need to do a particular job. We sort of want it to naturally figure itself out. So having the capacity or the number of EC2s we have in our cluster controlled by how much work we have backed up is one way to do that. This also means that spikes are no problem. So if we have a massive initial import and then we're incrementally doing updates, and then we have another massive import, nothing changes about our system. We don't have to tweak or tailor anything depending on volume. It just sort of scales up automatically. So one way we're using, just to recap, one way we're using auto-scaling is SQS to CloudWatch to power our auto-scaling capacity. So as we have more SQS messages, we just launch more EC2 instances and catch up. Each of those instances grabs a message and gets to work. What's cool is the reverse is true as well. As the number of messages in the queue falls, instances shut themselves down. So going back to our diagram, that allows us to get all of our raw data processed and put into S3 and go from this to this. So how can we make this cheap? And this is where I want to talk about the spot market a little bit, which is really has been helpful in this process. The spot market basically allows you to bid on unused EC2 capacity and get a really nice discount in exchange. Your instances run as long as the bid price that you've set is higher, greater than or equal to the market price. And the market price is determined by a variety of factors and at AWS, mostly based on demand. If the market price spikes, your instance is terminated immediately, which really plays in nicely with the make your messages short and repeatable, because that's when your messages are going to be failing the most, is when the market spikes and you lose all of your instances. And this is perfect for data processing, because in a lot of situations, we have a 12-hour delivery window or a 2-hour delivery window. It's not, we're not talking about seconds here. This isn't mission critical that we get this data processed. We would like it fast, because, and it also depends on the data set. But for this particular data, it's fine for us to postpone a particular task. So let's go through an example of how much we could save, how much we do save running on spot market. So this is an on-demand market price for a C3 X-large instance running in US East 1. That's the price on the website is 21 cents an hour. So if we wanted to run this for a month, that would be $151.20 per month. Now, if we look at the graph in the console for the spot market for this instance, we see that a C3 X-large in the same availability zone, that average price for the entire month is actually only 3.2 cents. It's drastically lower. So if we actually do that out for a month, that's only 23 bucks a month. Now, let's say we have 200 instances, and we run those instances all the time for month after month after month. Every month, we're saving $25,000. So this is the graph we just saw, but the graph isn't always flat. That's a lucky example. This is what we see a lot of the time. There's some weather, there's some turbulence on this in the market. So let's see what would happen if we set our bid price to $1.90. The first spike, we would lose an instance and it would come back on almost immediately based on the scale of this graph. That's a very brief spike. There's some longer spikes towards the end, but those are the situations where most of the time you're paying the price that is represented by the green line. You're not paying the bid price all the time. You're paying the price set by the green line, which is actually a really good detail, especially with this graph, because you can see that the average is pretty steady and pretty low. You're getting a really good deal most of the time. If you set your bid price here, even though your bid price is 60 cents, you're still only paying a little over 3 cents. But when that spike comes, you'll see that we cross that threshold and we will lose instances in that situation. Those first two examples are pretty tame. This one is where things get tough. This is a big, long spike, and let's say we had our bid price at the beginning of this set to 60 cents, and at that first intersection is when we lose our instance, and then we have days where the price doesn't come back down. And at this point, we would need to make a call. Do we wait for several days for the price to come back down, or do we bump up our bid price and get the work done? So best practices for the spot market, very similar to best practices for SQS. Keep your jobs small. They need to be repeatable. And just be prepared for spikes like the one we just saw. You'll need to either wait them out or increase your price. So we have these beautiful images. How do we get this data to users? So I sort of went through one example of data processing. I sort of want to move on to distribution. So just to give you a sense, we do, in the past 30 days, we've done 9.8 billion HTTP requests on our API. That's a lot of requests. Here are the distribution requirements for the Mapbox API. We need a massive amount of storage for that process data that we just generated. We need HTTP server capacity. Rather than image processing worker capacity, we need HTTP server capacity to serve this out to customers that we can spin up and down in the same way we can spin up and down workers. We need global distribution because our customers and our customers' end users are everywhere. And we use global distribution for both proximity, geographic proximity. We want to be down the street from our customers. Latency gets lower. And we also use it for redundancy. So if we lose a region or several data centers or access, if AWS has network problems or undersea cable gets cut, happens more often than you might think, we want to have several levels of redundancy so that our maps never go down. And then again, everything must be fully automated and low cost. So here's the tools we use for data processing. I want to change the last one. Instead of SQS, I'm going to swap that out for elastic load balancing. And here's the diagram that we were looking at for data processing. This last part of the diagram, the S3 bucket, is actually not just one S3 bucket. It's 9 S3 buckets. We leverage S3 not only as a storage platform, but a distribution platform. Because S3 is available in 9 regions, we get, by using all 9 of those regions, we get a built-in data cache all around the world, which is insanely valuable to us because it gives us a lot of coverage and helps us get to our end users faster. So each one of these dots is a AWS region. It's also, since we're leveraging AWS, we can also call it a Mapbox region. This is on our website, on our homepage. This is how we show our global footprint. Each one of these regions has 3 main components. We have an S3 bucket, of course. This is where the data is cached, processed data. We have an elastic load balancer, which basically takes requests, HTTP requests from an end user, and distributes those requests evenly over a cluster of EC2s. And then we have that cluster of EC2s, again, wrapped in an auto-scaling group. We're also using Route 53 DNS, latency-based routing, and failover to automatically send end users to the right region. This is really, really useful because if I'm in Australia, I want to be going to the Australia region, not to Singapore or Virginia. So Route 53 makes it very, very easy to configure this. It used to be a lot more difficult, and it's an amazingly easy product to use. So again, with data processing, we had SQS, CloudWatch, and then that plugged into auto-scaling. Now we have a different CloudWatch metric. That's the number of requests. That's the request count on the elastic load balancer. So basically, the more traffic we're getting, that metric goes into CloudWatch, and that influences the size of our auto-scaling cluster, auto-scaling group. And let's see what this looks like on our dashboards. You can see that the number of requests, sort of what Eric was talking about earlier, this rhythm. This is number of requests over 7 days for one region. And you can sort of see there's this night and day. You can sort of see night and day pretty clearly. So the number of requests graph could almost be overlaid over the number of instances graph. And this is how closely in lockstep those two metrics are tracking. Another example of this, just to show off how we follow the sun across all 9 regions. The tallest graph there, the tallest line, it's a little hard to see in the display, but that's our Dublin region. So that's EU West 1, and the second tallest line is US East 1, Virginia. The smaller ones are our more remote regions that are serving local requests there. But you can see how they're sort of offset. So just as Virginia is going to sleep, the East Coast is going to sleep, Europe's starting to wake up, and they want to see some maps. So in addition to just sort of to push it a little step further and squeeze even more performance out of our network using AWS, in addition to our regions, we also have a CloudFront CDN in front of our origin, our regions. And this gets us even closer to end users by putting cache edge locations, in a lot of cases, just down the street from our end users. So if a request comes in for an object that has already been requested recently, we don't even have to, it doesn't have to go back to one of our regions. It just gets served right there, and it's much faster. So how can we make this cheap? Slightly different strategy, because we can't use the spot market here. These instances have to keep running. So if the spot market were to spike, we would start dropping HTTP requests because we wouldn't have any capacity. So instead, we're going to use instance reservations. Reservations allow us to pay upfront and commit to using a certain level of EC2 computing. And we get to do that in exchange for a big discount on hourly costs. And we have seen that we're saving up to 60% or more in some cases, depending on the type of instance and the region. And I recommend doing this for any instance that you know you're going to be running and for any significant amount of time. So a few things that held us back. It took us over 2 years to actually buy a single reservation. We were a little hesitant to do it. We were constantly refactoring our applications, splitting applications up, launching new stacks, combining applications into two. And this all meant that we were adjusting our instance types because all of these applications have differing performance profiles, different memory needs, different CPU needs, hard disk needs. Some instances or some applications demand SSDs. And plus, at an event like this, AWS always announces new instance types. So the concern was, oh, we're going to reserve an instance type that's going to be obsolete. That doesn't seem like how the cloud should work. Well, it got a lot better. AWS recently announced 2 awesome features that allow us to swap reservations, any reservation within the same family. So if we want to get, instead of running 2 C3 X-large instances, we can trade those 2 in, or those 4 instance types in, we can trade those in for 1 C3 4X large. So that's the exact same amount of computing power. It's just like, how granular do you want it to be? So that made us feel a lot better because a lot of the instance type changes we were doing were on the granularity level. And then if you really want to get out of the family, so if you want to upgrade to a new family, you can sell your unused instances on a secondary market, and you tend to not get all of your money back, but you can recoup a lot of the cost by selling to another AWS customer on the third-party market. Finally, we found a great tool called Cloudability, which has an amazing, what they call a reservation gap report. And that basically gives you recommendations for instance reservations based on your infrastructure. And these are real numbers. When we first signed up for the account, we did the demo, and these numbers sort of were amazing. How much we would have to spend up front is a big number, but the amount of money we save over the course of the lifetime of the reservation, it was huge. Another important thing about reservations is when you go to buy them, you see the term 1 year used. So you think that you sort of have to commit to running the instance for the entire year in order to save any money. This is actually not true, and Cloudability makes it very easy to see that how untrue that is. In this case, there's a break-even graph to the right there. In this case, this reservation, we would break even in just over 3.5 months. And anything after 3.5 months would just be gravy in savings. We could shut that instance down and not have spent any more money than we would have otherwise. I've found that break-even points tend to be shorter for larger instances. that's all I had for data distribution. So these are the services that we just ran through. I did want to walk through one more example that I didn't have a slide for because Charlie just handed me this amazing card. Recently, the NAPE data that we processed, that was 8 trillion pixels. That was the 48 terabyte job that we saw earlier in the talk where we were packing up those hard drives. That was 10 years worth of computing. If we had run those jobs one at a time, that would have taken 10 years. But we did it in 2 days because of we were able to parallelize so much and run so much capacity in parallel. And because of the spot market, we were running on instances that normally cost 84 cents an hour. And if we had run that 10 years worth of hours, that would have been $73,000, more than that, $73,000. But the spot market gave us a price, instead of 84 cents, it gave us a 15-cent price over those 2 days for the same instance, and that only cost us $13,000. So that's 87,000 hours of computing only cost us, we saved 60K on that. So that's for one big bulk import. If you factor in several bulk processing jobs and then throughout the year, and then incremental updates to those data sets, you're looking at saving quite a bit of money with the spot market. And that's how we go that's how we generate beautiful images like this. A lot of credit goes to the Mapbox team. A bunch of us are sitting sort of in the middle back there. We're going to be doing a Q&A just outside across the hall after the talk, and I encourage everybody to come, and we have a lot of people from Mapbox here, so a lot of folks can answer your questions and just hang out over there. So thanks a lot for your attention. Thank you.